This is our 11.2. We will be talking about plate tectonics.
All right, so what does that crazy word mean? Basically, our planet has a bunch of land crust that is sitting on top of liquid hot rock that moves. That's it. So what that has done over time is it has moved these pieces of the crust, because it's not one whole big pizza, right? It's going to be different pieces of that big pizza that is our planet. And so the different pieces get moved along. And there's a great video, which we'll probably show you in class. If you click on this, the theory link here, it's going to take you to a very short video, but it compares plate tectonics a little loosely, not the best analogy, but good, to like a baggage claim situation at an airport. And so great analogies in there. Highly recommend it to take a peek. So let's get a little bit more technical here because we are scientists. So the lithosphere, or the Earth's crust, so these pieces of rock, are broken up into several different pieces, and we call them plates. They all have different names. You can see in the bottom corner here, several. We have a North American plate, we have the African plate, we have the Pacific plate, Antarctic plate, and so on. If you are interested in that and you want to take a look closer at that, this bottom link here, the plate boundaries satellite map, will show you where those plates are located and where they're currently at, which is kind of cool. And basically these pieces or plates move on what's called the asthenosphere, which is basically the deeper crust and that upper mantle, so that liquid hot rock that's moving around. And that interaction and that movement is going to be caused by a lot of different things, and it's going to result in a lot of different things listed here. So seismic, earthquake activity. There was just a big earthquake in the Pacific Ocean near Japan again. Volcanic activity and creation near those plate boundaries. The supercontinent formation and separation, which we'll look at next. And all sorts of other things that have been formed. Islands, fragments of continents, mountains, sizes of ocean basins, or the existence of an ocean, right? So plate tectonics really explains how the Earth looks the way it does. Like when you look at a map or a globe, plate tectonics is what got us here. And over time, again, we have evidence to show that this has happened. Plates have moved on our planet. And in the bottom right-hand corner, you can see a few different views of what and on the top for that matter, on the right, you can see several different views of where these supercontinents, so where the crust, the pieces of the crust were, and were they together, were they apart, were different sections together, and so on. So when this hot liquid rock, this mantle, this magma underneath the ground is moving these plates, sometimes they are moving towards each other, and sometimes they are moving away from each other. And so thus the pieces that sit on top of that move to and from. And that rearranges what our continents and how big and how small, like the Atlantic Ocean or the Pacific Ocean, are. A bazillion times in our history, we have had various different supercontinents, and we've listed a few here. Typically, this process is usually on a cycle of somewhere between 300 to 500 million years, and that these plates tend to move to and from, kind of like a yo-yo situation. All right, listed there: Valbara, Columbia, Rodinia, and obviously the one I'm sure you are familiar with, Pangaea. Those are all examples of supercontinents. So Pangaea is probably the one you learned about at grammar school, but that was just the last of many supercontinents prior to that. And Pangaea as a supercontinent started breaking up roughly around 200 million years ago. And that's what those pictures in the bottom right kind of show you. It shows you that breaking up process. It wasn't just one big split and they moved apart. It took, again, very long time, 50 million years, 25 million year segments for these continents, these plates to move. And pretty much right about now, if you're going to be around 250 million years from now, you may see the next supercontinent show up, because that's roughly about the time in which we will see that occur.
All right, so the plate tectonics are supported by a couple of different things, one of those being fossil records. So fossils are found distributed among many of the same continents. So like that picture there, you'll see some of the same fossils you'll find in South America, you'll also find in Africa. Evidence of glacier movement is found on rocks near the equator, and we know what we know about glaciers from it being cold and that deposit those glacier deposit in those different areas. We'll also find tropical plant fossils found in Ireland and Antarctica, so tropical plants in colder areas and places further from the equator help to support this idea of the shifting of the plates. And then the other one that supports our plate tectonics is seafloor spreading. So occurs on the seafloor where our tectonic plates are separating. Okay, so the newest crusts are found here at these locations, and the older crust is subducted back down into the mantle. So what's happening is it's recycling itself. So as it's flowing down into our crust, it is being remelted, and so that we can have some new crust layers above. As those plates diverge, heat from the mantle convection currents make the crust less dense, causing it to rise. And then the seafloor cracks and magma from the mantle rises up and it cools by the frigid sea water and forms what's called basalt, or that new crust.
And again, if you want to see that, we've got a nice little video here that kind of talks about seafloor spreading and kind of shows you where that's actually happening. I think they show the Mid-Atlantic Ridge, if my memory serves me correctly. Maybe.
All right, so some of our types of boundaries. Our first one that we'll talk about is the divergent plate boundary. So this is where a new crust is forming as the plates are separating. So think about divergent, they're going away from each other. All right. Here you'll see seismic and volcanic activity. So meaning we'll have earthquakes and volcanic activity there. Just like Ms. Laporte just mentioned, the Mid-Atlantic Ridge is an area where you can find this divergent plate boundary, as she's outlining there on that picture. The East Pacific Rise in the Pacific Ocean, and then as well as the Great Rift Valley, east coast of Africa.
On the top here, just so you know that this is like something you can actually go and see. This is in Iceland. And so basically this side over here on the right of this picture on the left, on the right of the picture on the left, this side over here, you are on the North American tectonic plate. And on this side over here, you are on the Eurasian tectonic plate. And by you, I mean me when I was there, standing there, which is pretty cool. So if you follow that Mid-Atlantic Ridge all the way up to Iceland, that's where you are at. You are at an actual tectonic plate boundary. And there's actual separation that's occurring, millimeters per year, but actual separation, and that movement is occurring, which is pretty awesome. Same if you were to go to the Great African Rift Valley as well, same type of situation occurring there. Eventually that portion of Africa will actually separate off and no longer be part of that, that continent. It's pretty cool. I mean, I guess it's not really cool, but it's interesting geologically. Some of the other boundaries. So these are all boundaries between different, when those pieces come together. If you want to think of them like puzzle pieces, you can. The next set of boundaries are called convergent subduction plate boundaries, and there are various versions. So I'm going to talk about each one of those. So the first is having an oceanic plate going against or versus a continental plate. And basically anytime you have something called convergent, like Ms. Kay said, divergent, all right, is separating. Convergent is coming together. So convergent plates are when they are, these plates are moving towards each other and then they collide in some way. And that collision, depending on which type of plates they are, oceanic or continental, that's going to make a difference in what happens at that collision. So let's get a little background. First of all, oceanic plates typically have greater density. So they're going to have more rock packed in together. So they're going to subduct under, so slide underneath the continental plates, which tend to have lower densities, all right, not as many rocks packed into the same amount of place. And so what we see happening here, you can, again, outline it on your notes as well. We form what are called trenches, and we'll show you what that looks like here on the bottom right, or volcanic mountain ranges that you might have at those boundaries. And here you can see the list of various places on Earth. So the Andes Mountains here on the west coast of South America. All right, you have an oceanic plate, Pacific Ocean, and this South American plate here undergoing convergent subduction. We have White Island in New Zealand, where you're also going to see that. And then the Cascade Mountains in Northwest United States. So that's over here, the Cascade Mountain Range. I think Case has been up somewhere there. Yes, no? Yeah. So in that area as well. And then here's what we see with that, that trench being formed. All right. So we can see the oceanic crust, more dense, is going to slide under. And then that continental crust is essentially sliding on top. And so you end up with this very deep area of the coastal area in most of these places. And you can see a huge line of volcanoes that form in that area. And if you are familiar with any of these places around the world, you can see the high number of volcanoes near those types of boundaries. So that's our first convergent subduction. The next is we could have two oceanic plates come into collide and go against each other. So again, the same process is occurring, but now we have two oceanic plates. So their densities are they're going to differ by age. So the older oceanic plates are going to be more dense because they'll be a little cooler. And so they are going to slide again underneath the less dense and younger plate, oceanic plate. And so again, we're going to get those trenches like we saw in the previous example and those volcanic mountain ranges. But these are obviously going to arise out of the ocean, all right? And they're going to be called island arcs, all right? And so we can see that here in Alaska. That's called the Aleutian Peninsula in Alaska. And you can see a bazillion volcanoes here, all right? Right in this place where we have our two tectonic plates coming into collision here, two oceanic plates, I should say. And so there is huge amount of volcanic activity that takes place in that area in Alaska. You also have the Mariana Islands in the Western Pacific, and that is part of something called the Ring of Fire. Yes, Johnny Cash sang it well. It is essentially this whole rim all the way around the whole Pacific Basin that basically has a bazillion and a half volcanoes. Highest level volcanic activity is going to be in what's referred to as the Ring of Fire. And the Mariana Trench occurs here in the Pacific Ocean, and as a result of those two oceanic plates coming together, right? The Caribbean islands, if you've ever vacationed there or cruised there, those were created as another island arc from oceanic to oceanic convergence. So again, earthquakes and volcano activity here for sure. And last but not least, in terms of convergent, we have another type of convergent plate boundary, and that is convergent collision. Right. So what is happening here is no more oceanic plates. They're out, and it's two continental plates. So this is two younger, less dense continental plates, again, moving towards each other and colliding. Well, they're both continental plates, so they're already going to be less dense. They're going to be very buoyant. So nobody's going to want to sink. Nobody's going to want to subduct underneath or slide down. And so they're going to be kind of evenly matched. And basically, they really collide, all right? The other ones we called a type of a collision, but not so much. They really are going to collide, and what happens when that collision occurs, because neither one gives way, is that the crust starts to crumple up and then gets pushed upwards. And basically, we get these really awesome mountain ranges that we have. So two of the most famous that are the result of convergent collision boundaries are the Himalayan mountains. And the Appalachian Mountains here in the United States. So there's your Appalachian Mountains in the upper left. And then those are on the east, near the East Coast. And then you can see a nice picture of the Himalayan Mountains there on the bottom. And there you can see, again, that kind of crunching of that continental crust.
All right, and the last is the transformation or the transform plate boundary. This is when the plates are sliding past each other. So they're creating a type of friction. So they're just rubbing up against each other. No new crust is created here, and no old crust is being recycled. And because of this friction, where it's creating faults or cracks in the crust, and these are creating seismic activity. So that means that we're having some earthquakes here. There are no volcanic activity going on, and some of the most notable ones are the San Andreas Fault in California. And the other one is the Alpine Fault in New Zealand.